Okay. Hi, welcome. My name is Jim Dowling. I'm the CEO of a company called Logical Clocks. We're based right here in Stockholm. And I'm going to talk today about deep learning. And I'm not just going to talk about ordinary deep learning, but I'm going to talk about distributed deep learning. So when we scale it out with many GPUs and many servers. And I'm going to talk about a platform that we've been developing called Hopsworks. It's an open source platform for data and AI. And at the end, I'll give you a link to it so you can use it for free. So we have actually a cluster up in Luleå sponsored by RISE, which is a research institute of Sweden. And they have a nice cluster up in Luleå with a bunch of GPUs, and you can get access to it if you stay until the end. Okay, and if you stay until the end and decide to ask a question, please come up to the mic and ask the question from there. Okay, let's get going. So what's been happening the last few years is that we've seen a lot of interest in AI. Why? Well, because we made some massive breakthroughs. And to be frank, and I taught the first course in deep learning in Sweden. I'm also an associate professor at KTH. The history of a lot of our modern AI started in 2012, because that's when we showed standout performance in object recognition in images in the ImageNet network. So the innovation of AlexNet was that they actually used GPUs to train deep neural networks, and they massively beat the state-of-the-art object classification algorithm in image processing. So since then, we've seen massive improvements and state-of-the-arts reached in a number of different areas. You can see there's natural language translation. We now have the best systems are available in deep learning, and lots of other fields, self-driving cars, we've seen massive advances, and of course, systems like AlphaGo, where the world's best Go player was beaten by a DeepMind system. So what's interesting about this is that the amount of compute you need to train the state-of-the-art AI systems has doubled every 3.5 months since 2012. Now, if you're familiar with Moore's law, that's where the number of transistors on a CPU doubles every 18 months. This is a far steeper curve. And NVIDIA are not doubling the number of transistors on every GPU every 3.5 months. What's happening is that we've gone distributed. So sometime around 2015 or 16, what happened was the state-of-the-art systems went from using one GPU to hundreds of GPUs in the latest systems. So one way of capturing this, and if you follow the state-of-the-art conferences in deep learning like ICLR, it's all going distributed. We're getting bigger models, more data to train them, more compute to train them. And we're pushing out the state-of-the-art in a lot of areas with techniques such as AutoML. Now, this morning, if you attended the keynote, Ellen Friedman said, well, I don't know any areas where computers or deep learning systems are outperforming programmers. Well, I do, right? Because if you look at the state-of-the-art in terms of most of the tasks around deep learning now, they're auto-tuned. So you have an algorithm. It could be a genetic algorithm. It could be a reinforcement learning algorithm. But they're building better deep learning architectures than humans are. And so that means basically if you're a data scientist, you're the first official job to be made obsolete by deep learning, because now the computers are doing it better than you. But what you need to do that is you need lots of GPUs. You need lots of compute. And you need then the algorithms and infrastructure to support you doing that. Now, I'm not going to just talk about distributed deep learning from the perspective of training models with lots of GPUs, and that's very important because deep learning and machine learning in general is about building systems. So if you're interested in adding machine learning to your product, you will have a data product because you're going to have data. And somehow you need to integrate that into an entire pipeline. And what Google had quite a famous paper called The Technical Debt of Machine Learning. And what they wanted to point out was that the model training part, the part that many people consider to be deep learning, the part where you take a GPU to train a deep neural network on some training data and output a model, that's just one small part of the bigger picture. So there is a high technical cost to setting up deep learning systems and machine learning systems. And what you can see here are just a number of the services that you need to do that. So it's not enough just to manage your GPUs on the left. You need to also make sure that your data comes in, that you validate the data, that it's not incorrect, that you extract the features from that data. And then when you do your training, you might need lots of GPUs for distributed training. You might need lots of GPUs to try and find good hyperparameters more quickly. And then you need to orchestrate the whole of these pipelines. And when you've finished and you've finally gotten some models, you need to serve them, make them available to applications. And it's not just enough to serve them. You need to monitor, make sure they're performing well. And when you want to deploy a new model, you want to test it out with A/B testing before you actually run it in production. So I'm going to talk about the whole pipeline, not just about the training part today. And the other piece of the puzzle that we kind of need to add in is really big data. So it's not enough to have lots of GPUs. You need to have a lot of clean training labeled data. So we're talking about supervised machine learning here, and you have to have GPUs. I'm just going to make that point again because it's not always clear when you hear people saying we've had machine learning for 20, 30 years, 50 years, which we have. But the breakthroughs we've made are in deep learning, and you need GPUs to train deep learning systems. So one way of looking at building data products around deep learning is that you need to first, on this Maslow's hierarchy of needs, you need to first manage your data. And once you've managed your data and you can extract features from the data, only then is it worthwhile to actually do deep learning. Now I'm going to talk a little bit about our platform. It's called Hopsworks. And I tried to start out, from a very simple kind of overview of what the platform is about. It's a data platform, so it's actually a next generation Hadoop platform. And with data, what I mean is support for batch and stream processing. And for deep learning, that's what we call AI, we support things like GPUs, which you will need to do deep learning, and also frameworks that you need for deep learning. So the platform is a stool, and it has these three legs. We have the ways of getting data from stream processing, batch processing, and then doing our training and our model serving with deep learning. So to put a little bit more meat on the bone there, if you start on the left-hand side, you can think of it as being we have data coming in that we're going to somehow process. And if we're doing batch processing, typically what the batch processing will have is it will take the top row here. We're going to have a scale-out file system, HopsFS, and we're going to do our Spark processing and Hive for our data warehouse, and then have our BI tools for reporting. This is a pretty traditional data analytics stack, but you also need more modern stream processing. And then the bits that I'll talk about a bit more today, which are kind of, I guess, more novel, is the feature store, which is a new data layer that we've introduced for managing your data for deep learning. And then the model serving and the training itself. You also need to pull these things together with Airflow that I'll mention in a bit. Okay, so this is we're still at a high level of abstraction. If you want to talk specific frameworks, you can think of a machine learning pipeline as ingesting data from somewhere. It may be clicks on your mobile phone, it may be searches on a website, it may be tracking you on Facebook wherever you go. It's data coming in from somewhere, and there are lots of frameworks out there to ingest data. The ones that we support are Kafka, and we have a REST API in our platform. So you can ingest data with certificates to either Kafka or the REST API. And once you've got it in, you have different frameworks for processing your data. You can use Flink or Spark. You can even use TensorFlow. So many of you might not know, but TensorFlow has support now for doing data pre-processing. The only problem is it works on one server, not on many. So it doesn't scale out. And then finally, when you're next stage is when you're storing your data. We have our own HDFS version called HopsFS. We also have Hive, which is a data warehouse, and the feature store that I'll get into some detail on later on. So this is where we're going to manage our data for training and doing experiments, and then you need some frameworks. There are lots of frameworks out there, but to be honest, if you're new to the field, there's only two that are really significant. One is the top one, Keras and TensorFlow. They really become one framework now. And then the bottom was PyTorch, which is making a lot of inroads, particularly in research. Once you're able to train your models, you need to maybe do experiments with Jupyter notebooks, and you need to serve your models as well. So I'm going to mention a little bit about TensorFlow serving as a way of taking a model trained in TensorFlow and making it available to applications to make predictions on that trained model over the network. Okay, so and then at the bottom we have a way of integrating all this together with Airflow, because even if you have a pipeline, you still need to somehow put all the pieces together. I'll mention a little bit later. Now I'm going to take a step back and get a little bit more abstract. That's kind of the bits we have, but we're not the only vendor or open source project in this space. And if you're doing machine learning at scale, you have to build a pipeline from when the data is collected or ingested. Typically your data will need to be transformed. You need to verify that that there's no empty columns or null values that might cause problems training. We need to extract our features because we're going to get data from many different data sources. And then we need to do a period of experiments to find good models, train those models, test those models, and finally serve them in production. And you'll often need some form of distributed storage to knit the whole thing together because you're going to be storing state along the way, and you need to read up data and write it out and read it up again. Now, if you want to do this in a scalable manner, there are a lot of potential bottlenecks. You could do all of this in a single TensorFlow program if you wanted to, most of it in any case. But if you do decide to do it in a TensorFlow program, you'll be running on a single server. And depending on the amount of data that you're processing, this may be a bottleneck. If you only have one GPU, this can obviously be a bottleneck when you're training or doing experiments. It can slow you down a lot. And if you're going to serve models, and you're going to have lots of concurrent clients to access those models, if you just run one standalone TensorFlow serving server, that can become a bottleneck as well. Ideally, you'd like to have lots of them running and load balance requests over many of them and have them scale in and out. So we'll see how we have Kubernetes to do that later on. And the final part, which may not be obvious as a potential bottleneck, is the storage layer that you're using. So if you're going to train a image classification system with lots of small images, you may have 1 million images, and you're storing the images in S3, and then your deep learning system is trying to read the images, and your GPU, the V100 from NVIDIA, it can process 150, 200 images per second or even more, and S3 can't keep up. If you go to S3, you wait, and even if you do batching of requests, it may not be able to keep up. So you have to consider that when you're designing your system, to how to get around limitations of your distributed storage layer. I mentioned that we're not the only solution in the space. I guess the most mature one is Google Cloud. They have something called TensorFlow Extended. And TensorFlow Extended is the TensorFlow that you know, but what they're promoting is technologies for doing the data validation, the data transformation with lots of servers in a distributed manner. They're saying, well, you should use Apache Beam. Now, if you've never heard of Apache Beam, it's a data parallel programming framework. It runs on top of Google's own data flow engine. It also runs on top of Apache Flink, so we're supporting it in our platform. But the programming model is a little bit different. I would say the dominant platform right now is Apache Spark for doing this. And Google have to convince people that they need to move from maybe tools they're familiar with, such as Spark, to Beam. And that's a process that's still they're still trying to push. And they haven't really done much on monitoring yet. So, but TensorFlow Extended is a very interesting model that they're promoting for doing these machine learning pipelines at scale. Amazon doesn't really have anything right now because they've been pushing MXNet, and that's obviously not going to work. So they'll need to refocus and decide what way they want to push it. And Microsoft haven't really got sorted out either because they had their own framework, CNTK, which they abandoned recently for PyTorch. So the obvious way to go about it is to say, well, this Beam thing isn't really, it's not really mature. It doesn't really have a wide adoption. Let's use Spark instead. And we like Python. We want Python the whole way. I don't want to ever have to leave the Python language. So let's take PySpark, which is a data parallel programming model in Python using Spark. And then let's run distributed TensorFlow. And Kubernetes seems like a good option for serving models because we can scale up and scale down the number of model serving instances we need. So the only thing about this particular approach, and this is the approach we take actually, is that there's one big caveat emptor, which is that you can't go directly from the PySpark program into the TensorFlow program, because in Spark we have an abstraction called a data frame. And in Spark, the data frame is a data structure that's kept in memory on the executors that run. And there's no way of just pushing that directly into TensorFlow programs that are running on GPUs. Right now, there's work ongoing in the Spark community to try and get around this, but right now there's no way of doing it. So what we do instead is that we say, well, let's have a file system layer, the layer at the bottom called Hopsfs, and let's just run our programs to do the data transformation, the data preparation. Let's write out our data to this thing called a feature store. And when we want to train models, we'll just generate training data from all the features that are available in the system. And that training data will go directly into our deep learning platforms, whether it's Keras, TensorFlow, or PyTorch. And when we've trained a model, we'll write that model back out to the same distributed file system. From there, you can serve it in Amazon or in Kubernetes or wherever. While we're training, we'll generate a lot of logs and experiments, and we'll make them available via things like TensorBoard. So this is the approach we're taking, and what you may understand at this point is that, well, this is not one program. This is not one pipeline program. This is lots of small programs. You know, we have a program to push data into the feature store. We have a program to take from the feature store and generate training data. We have another program to train the models. And you can use Airflow. So in our platform, we're promoting Airflow as a way to knit all these parts together. So Airflow is an orchestration engine. And you can basically say, run the pre-processing Spark ETL job. If that completes successfully, then let's do our distributed training. And if that works, let's test and validate the model, send it for serving, and then let's start monitoring the model when it's in production. So that's the basic kind of overview of how we're trying to approach the problem. Now, I mentioned we have a feature store, and I'm going to just talk a bit about it. It's a new service we have on our platform. We have the world's first open source feature store. There's a bunch of companies who have feature stores already, but they're not open. Uber, Twitter, Airbnb, Comcast, and so on. And what Uber said about their motivation for the feature store was that the biggest problem you have when you're building these big distributed pipelines with data coming in and training of models and then serving of them is that the data scientists, who are very expensive to work on, they spend a lot of their time trying to find the data. Maybe it's a CSV file here, maybe it's a database in the warehouse, a table in a data warehouse, maybe it's a Kafka topic, and then putting all the data together into the format that you need to train your models with. And this is quite a time-consuming, difficult problem. So broken data is the most common cause of problems in their production ML systems. So these first three steps we see in red here, data collection, transformation, validation, and feature extraction, we encapsulate that in a single service we call the feature store. And what the feature store is basically a central data layer where you can say, here is a feature. Now, I'll give you a quick example of a feature. Maybe I have a data warehouse, and the data warehouse says, the user registered on this date, and then another column says the user used the product first on this date. So we have two different columns, one when the user registered, one when the user first used the product. But in machine learning, we might want to use a feature called what was the time between registering and using the product. So that time between the two events, when I registered first and when I used the product, that's what I want to use to predict with. That particular feature may not be in the data warehouse. You'd compute it. You compute it by reading the two columns and subtracting the time you registered from the time or the date time when you first used it. Now, what a feature store will do is give you that available as an abstraction. We have the time between registering and first using the product. And we can then have a version for that. We can have documentation for it. Data scientists can go into a single place where they'll discover all the features. And we can automatically backfill the computing of these values. We can have jobs that run every hour that fill up all of this values for all the users. Most interestingly here, though, what we can do is we can make sure that that feature is reused across all the programs, because currently they're not being reused. What's happening is someone in some program, in some particular application will develop that feature, put it in their pipeline, and somebody else will develop it in their other feature in their pipeline, and the two things will be completely separate. It can be even worse than that, because you may have a feature that's used for training that's implemented differently when you're doing production serving, and that can cause the model to badly perform. So Uber have about 10,000 features in their feature store, And what they notice is that as you add more and more features to the feature store, the cost of doing machine learning decreases, because you don't have to spend all that time looking for the data, pulling it out, implementing the features. Once they're there, you basically you get a vastly reduced cost in developing new models and experimenting. So this is kind of what it looks like when you don't have a feature store. We have, if you look at the top, we have 4 different applications. 3 of them are training neural networks, and one of them is a deployed or model serving. And you can see that what we have in bold are features that are duplicated across those 4 different applications. That means they're re-implemented. You can see all of them are pulling in data from different data sources in our data lake down here. But what we end up with is non-dry features and redundant features, and no way of finding out what features are already available in these applications, because you would have to look in the code to see what's in there. And there's no easy way to pull out that feature from that code. So what the feature store is doing is introducing this new layer where the features are documented, versioned, and available. And then we'll have an API to search for them, to add new features, to generate training data from these features, and to backfill feature data so they can be reused. So the abstractions that you have to think about as a data scientist when you have a feature store is that at the very bottom you're going to have features. And I mentioned one already, the time between registering for a product and first using it, but you could have another feature which is just the customer profile data. So maybe the customer has some score, or maybe the customer has a date of birth. You can have lots and lots of features, and what we do is we group the features together. And typically this is because we have a job or an application to generate the feature data. And the group is really the job that generates all of the features within the group. But what a data scientist will do is we'll say, well, I'm going to train a new model, and we'll look through all of the features at the bottom and say, I want this one, this one, this one, this one, this one. Please generate me some training data. And that's this training data set D, and that's what they'll work with when they want to train a model. And that's vastly improved over the data scientist going down to the data lake to look for CSV files and extract data and columns from tables and topics from Kafka. I'll show the API in a second to make it a bit clearer. But the building blocks for this feature store are that we need a storage layer, which is our HDFS, for storing the feature data. We have metadata for the features, describing the versions. I'll show you some analysis of the features as well. We can compute statistics over features, max, min, average, and so on. We can have documentation and jobs that generate the feature data. And then we have a registry of all the features. So the company will know which features are available, and they'll be kind of governed and securely accessed. And then finally, the applications that generate the features or that consume the features, the ones that write to the feature store or read from the feature store, will use the API that we define. So just to give you an idea of the technologies, the way you generate a feature is that you would either use a Pandas data frame or a NumPy, or a Spark data frame, and you would basically pull in the data from your different sources. So it's typically a data engineer who does this, and they'll write out that data as a feature group. And that data will be stored in Hive in our case, and the metadata for those features we store in a backing MySQL cluster NDB database. And this is the API, just to make it a bit clearer. So at the top, we have what a data scientist is doing now with the feature store. The data scientist looks for all the features and says, I want average attendance and average player age as the features I want to make my predictions with. And they get back a data frame. And with that data frame, they can then generate training data, and then you can train a model with that clean training data that you know has been validated before it's put in the feature store. If the data scientist says, I need a new feature that's not available in the feature store, they might sit down then with a data engineer and say, okay, we need a new feature. Well, what the feature is going to be is we're going to take in this file name, which has some data, and we're going to generate polynomial features for it. So we're just going to take the power of 2 of the feature values. And this particular, you can see this particular job, what it's doing is reading up this data frame, and it's taking every value and squaring its value. And then it's going to say, this is a feature now available in the feature store, and it's called polynomial underscore feature group. So now if you wanted to include that at the top, you could just put in comma and then inverted commas, polynomial underscore feature group, and it will be another feature in your training data for that model. Okay, so now we've kind of gone through the kind of data prep part. When we get to the distributed training and experimentation, what that means is we want to use more than one GPU to make sure that we can either train faster or better. We want to do better experimentation, maybe better or faster. What can we do with lots of GPUs? Well, we're going to use PySpark for this. So the first thing you need to have is you need to have a resource manager that gives you GPUs. Spark itself does not know about GPUs. It doesn't have an abstraction for GPUs. We have a small change to Spark to tell it about our version of Yarn that has support for GPUs. But Kubernetes has support for GPUs and Mesos has support for GPUs. So your PySpark application has to say, give me 10 GPUs or 100 GPUs or 1 GPU. And once he has GPUs, off it can go and do its thing. So in our case, how that works with PySpark is that a Spark application or PySpark application consists of something called a driver at the top, and then you have one or more executors at the bottom. Now, this may seem a bit abstract. They're going to be containers if we're running Yarn. So we'll have a driver. It will have no GPU, but the executors will all have GPUs. So if I want to train a very large job with 100 GPUs, I'll get 100 executors, one driver. So what the code would look like, to give you a very simple example where we're using GPUs, is something like this in our platform. So this is a Python program. We have a function defined called executor, that's def executor, and we're printing out inside that saying, hello from GPU. This is where the GPU code runs. So inside our function, we're going to be inside this executor that I showed you earlier. And in the global scope, the next two statements from hops import experiment and experiment.launch executor, this particular code will run on the driver. And it looks something like this. If I have two cells in my Jupyter notebook, the first one will define the executor function, and the second one will define my driver. So if I run with one executor, the code will run as such, but if I run with 4 executors, it's going to run on 4 different containers in the cluster. And if I run with 100, it'll run with 100 different containers throughout the cluster. Now, one of the problems with PySpark has always been, how do I get my Python libraries onto these executors that are going to be out there? And people are looking at Docker as a way of doing that. We have a slightly different approach. What we do is we deploy Conda environments at every host in our cluster. And for every project that this particular program will run inside, there will be a Conda environment for that project. So if you install a Python library in your project, it will be available inside the executors. And you can just use them as if that's been pre-installed. So what it kind of looks like from a UI perspective is something like this. You have a bunch of libraries already in your project, and you can go to pip and install a new library, and then it will become available in your application to use. The other thing that you need that isn't always obvious if you've come from a kind of Kubernetes-style background is that a file system, a distributed file system to coordinate all of these executors running is very, very important. And the reason why it's important is because it can do everything like manage your large volumes of data, your training and test data sets, which may not fit on a single server. It'll do model checkpointing as it runs. All the executors will checkpoint, or at least the head one might generate the checkpoints. You can output the models that you've trained for serving. You can maintain state while you're doing distributed training or parallel experiments for coordination. The TensorBoard logs will be in the distributed file system. If you don't do this with your file system, it becomes very, very hard. You end up doing a lot of microservices and trying to transport data from all the executors once they're finished. It's not pleasant. So the only negative point about file systems that people will say is, well, distributed file systems are great, but Uber said, well, we're doing self-driving cars, and we're generating a lot of images, and we just can't read them fast enough into our system. So what they said was, we develop a whole new file format called Pedastorm, which is really just Parquet with some more metadata. And we'll put our images inside these bigger Parquet files. The problem, of course, now is that you can't look at your images. There's no tools to extract the image from Parquet, to read it and visualize it. We've solved this problem. here at KDH and Rice and logical clocks. We've added support for a new type of hardware called NVMe disks. You may have heard of them. They're SSD disks, but they connect to the PCI bus with a new interface. And the thing about NVMe hardware is that it's actually an order of magnitude faster than normal standard SSD disks for things like random I/O, disk I/O for IOPS. So that we asked ourselves a question as researchers a couple of years ago: can we add these really cool new disks to our file system, our HDFS called HopsFS, and make it support them? And the answer was yes. And the way we did it was that we worked with Spotify and we looked at their distribution of file sizes, and we looked at how many operations were on different files of different sizes. And we saw that 1/3 of their files are small files, under 64 kilobytes in size. And 42% of the operations on their files are on files even smaller than that, even less than 16 kilobytes. So what we said was, well, why don't we put the files in our metadata layer where we can put the small files on these NVMe disks. So we're going to take a file that's under 64K or 128K, it's configurable, and put them on NVMe disks in the metadata layer. And we did that. And some of the throughput improvements that you can see here, up to 66 times faster than HDFS for writing small files. And on real-world workloads, we've got some really nice improvements in both throughput and latency. So we can handle things like Uber's problem of, I have 10 million or 100 million or a billion files, small files, and I can't read, my file system slows down the training of my deep neural network, so we don't have that problem anymore. Okay, next part. We're still on this area of distributed training and experimentation. And the first step you kind of do when you're doing experimentation is that you want to find good hyperparameters for your models. And hyperparameters are parameters that you do not know in advance of training. You don't know what they should be. You can guess, you can read a paper to find what hyperparameters they used in that really state-of-the-art paper. But there's no theory available for us to decide on how to set good hyperparameters. So a hyperparameter might be a learning rate for your algorithm, the rate at which it updates the weights with stochastic gradient descent. How many layers in my neural network might be another hyperparameter. Like I said earlier, humans would typically do this, but machines are now doing it better. So what you can do in our particular platform, for example, is that you can run these executors. On every executor, you do a different run of the training algorithm, but with different learning rates. That's LR, and maybe a different number of layers. And then you measure the performance of all the different experiment runs. And you see which one is best. And then you adapt the hyperparameters for the next run of the experiment to try and get them better. Now, you can use algorithms like genetic algorithms or reinforcement learning to automate this process. We call that auto ML. But the point is that if you have enough GPUs, then you do this, and it saves you having to pay an expensive data scientist who's going to take a very long time to find good hyperparameters. There are some small optimizations you need to do, like we have blacklisting of executors in Spark, and we use dynamic executors, and that helps us, optimize resource utilization. But really, it's not more complicated than that. So this may look complicated. If you look at it on the screen, you'll see, hey, he's got 6 servers or 6 containers, 6 executors in Spark. And if he goes to 60, he's going to have 60. Do I get 60 times more code? Well, the answer is no. You get no more code, because this is the code that will run it for you. And what you do is you basically decide how many executors to have at the beginning, and you start it. And this particular example is called it's called grid search. I can see it says experiment.launch, and that's actually old code. So it should be experiment.grid_search. And what it's doing is it's going to call the function train, which is written in yellow there. And you can see it's passing argstict as a parameter. This is a Python dictionary. And it has 6 different combinations of hyperparameters. There's learning rate 0.001 all the way up to 0.1, and dropout rates of 0.5 and 0.6. So if you compute the combination of learning rate and dropout rates, you get 6 potential combinations. So it runs 6 different experiments, and if you start it with 6 executors with 1 GPU each, they'll all run in parallel, they'll all compute their error, their prediction error, and then you get a result and see which combination was the best. This algorithm grid search is, it's quite simple. It's a good way to get started. You can use, like I said, genetic algorithms if you want to get a bit more sophisticated. We actually have some examples with genetic algorithms if you're interested in the. We have a tour that you run when you log into the platform. So that was the parallel experimentation. But what if I have lots of GPUs? Does that help me train my models faster? It does, is the answer, and it does because you can use an approach called data parallel training or synchronous stochastic gradient descent. And what happens is that you have a model you're training here. We can see the training time there, and we have a certain slope on the training time. And we want to minimize this thing on the y-axis, the generalization error. And if we ran on that one server, it would take quite a long time to train. But if we add servers, we can see the training is going faster. The slope is increasing on this, the amount of time required to reduce the generalization error. So, you can, just to give an example of how much you can reduce training time by, there is a well-known data set called ImageNet for image classification, and it has 1 million images. And I think 3 years ago, it took 2.5 weeks to train that. Latest result I heard was 190 seconds to train it with 1,000 GPUs. So, if you can reduce training time from weeks to seconds, that changes how much work you can do and the types of problems you can address. A little bit more technical, what does this look like, data parallel training? Again, you need a distributed file system to coordinate the whole process, and each GPU will have a copy of the model, and they'll read in part of a larger batch. So if the batch is 3,200 images, and each one gets 32 images, they'll compute the changes in the weights, we call those the gradients, and then when all of the GPUs are finished, we'll aggregate the results, compute a new model, broadcast it to all of the GPUs, and then we'll go again. And this is the thing that this is the approach that reduced the ImageNet training time from weeks to seconds, data parallel training. So how do you do data parallel training? I showed you the hyperparameter search approach, and that was pretty straightforward. If you go to TensorFlow and read up on it, they'll tell you about something called distributed TensorFlow. It has parameter servers, and you put your parameters on the parameter servers, and the GPUs run at the bottom, and then they talk to the parameter servers, and you have to do a lot of work yourself in something called tf-config objects, setting all the IP addresses. It's very messy. A framework called TensorFlow and Spark by Yahoo tried to help you with that. To be honest, this is old stuff. Don't touch it. Go with ring all reduce. This is the algorithm that people are using that scales. In the previous, this model, the parameter server model, they become a bottleneck. So the training will only get better up to a few servers. After 3, 4, 5 servers, it bottlenecks. Or 3, 4, 5 GPUs, I should say, not even servers. Ring all reduce is bandwidth optimal. And you build a ring, and each server in the ring, which is a GPU, represented as GPU here, will compute its gradients, send it to its neighbor, and receive the gradients from its neighbor. So all of the gradients will circle around the ring, so you're using both the upload capacity and download capacity of all of the containers or servers in the system. And it's available in 2 platforms. Horovod is one by Uber. It's a framework on top of TensorFlow. And since TensorFlow 1.11, there's a new native version called TensorFlow Collective All Reduce. And in Collective All Reduce, by TensorFlow, again, we have this horrible tf-config thing. You're supposed to know all the IP addresses of all your processes and put them in this tf-config object along with the GPU device IDs. Nobody is going to do this. So we do it for you. We do it with Spark, that we run the Spark with to start the executors, and they know the GPU IDs, they know the IP addresses, and we build up this tf-config so that you don't need to touch it, and you don't need to even know about it. So we'll automatically build a ring and allocate the GPUs to Spark executors. Now, the way you typically program in these models is that there are higher level APIs in TensorFlow, not the lower level datasets, layers APIs, something called estimators. Now, if you haven't seen an estimator, I'll just show you one. It kind of looks a bit like this on the left. It's a very oversimplified code. We have notebooks with the full examples here. But on the left, we can see we have tf.estimator.run config. This is the run config for an estimator. But what we can do inside it, which is really nice, is that we can say, hey, the model will be output to this particular folder, the TensorBoard logs will be put in this folder in HDFS, and the checkpoints will be put in this folder in HDFS. And now we're going to run our distributed training with experiment.collectiveAllReduce, and that will store some more data in the file system under the same path. It's been clipped a little bit there. So the code for distributed training is not that bad. This is an example with just Keras and TensorFlow. And it's obviously massively oversimplified, but we call experiment.collectiveAllReduce. This is our distributed training function. And we have to set up our run config to use collective-all-reduce strategy, and we have to use the estimator then to do the training. But otherwise, it's very simple to normal estimators. So again, if you're training this on one GPU, it's the same code as training it on 100. At 100, you'll probably get some sort of slowdown because of network bottlenecks, but that's what you get to experimentally. So so now we've gone through experimentation and distributed training, but there are a couple of other things you need to care about when you're running these pipelines. I ran these experiments, like, do they just disappear when I've finished? How do I go back in time and see what happened when I ran an experiment? So what we do is we actually store the experiments, and we store them. You can see there's a service here. It's based on Kibana. You can see your experiment that ran there, and there's a TensorBoard available for that experiment you can look up. And if you click on it, you'll get details about your experiment, and you can pull up the TensorBoard for the experiment that ran. And you can see here we have one that ran some hyperparameter optimization. You can see there's lots of different lines with different colors. These are different parallel experiments that ran. So that's kind of nice, because then now you have a history of what's happened, and you can go back and say, well, what happened last month? Well, I did all these experiments, and these were the results I got. So once you've done your training and you're happy and everything's good, you need to then serve your model in production. You need to put it out there. And we support model serving in our platform, and we do it with TensorFlow serving primarily for deep learning. You can do it with Spark as well, with MLeap, and scikit-learn also has some support. But the kind of features that you want to have in here are things like a canary to make sure that the serving is going okay, support multiple models for A/B testing, and then you want to increase and decrease the number of instances if the load increases or decreases. Now, Kubernetes, we use Kubernetes for this, and in Kubernetes you can have your model behind a load balancer, which gives you the scale up and scale down properties. You can configure it to add more model serving instances. They're going to run on Docker containers as needed. And you can access that natively. If you're within Kubernetes, you can go straight down and access that with an internal application. But if you're something outside and you want to have security and logging of the request for your model serving, what we do is we go through the Hopsworks platform. It has a REST API, and it redirects to the Kubernetes instance, and it also logs the requests. And it's not just enough to log the request. We want to know what the prediction was, because at some time in the future, we might find out what the actual result is. And then we can join together the prediction that we made here with the actual results, and then we have new training data that we can use to improve our models. So it's important you capture the data as it flows through the system. We're doing this by using Kafka, so the requests get logged to a Kafka topic, and then a Spark streaming application can then process the data as it's coming into the topic in Kafka. You can do things like notify people if the model seems to be performing poorly, or even kick off retraining if needs be. Now, I think I have a couple of minutes, so I'll show you a quick demo to give you a feel for what this looks like, because it's all been very abstract. The platform does support a REST API, but it's also a UI. So data scientists will work with our user interface. If we come in here, let me see. Okay, so this is the platform as you see it when you log in. We have something called projects over here, and we have tours to get you started. So if you can create an account on our platform later. I'll show you the link at the end. I'll just show you the feature store to give you an idea of how that looks like. So we have a bunch of services here. We have our Python libraries that were installed. This is Python 3.6, and you can see the installed libraries there. But the feature store, which is a new feature, or a new service that we have in the platform, you can see that we have a bunch of feature groups here that we see. And we have jobs to generate the feature data, and you can have features that don't have jobs. You can look at the statistics for any feature or feature group. You can say, let's have a look at the correlations between the features. Let's have a look at any clustering over the features. This will be automatically computed by our framework, actually, when you register a feature. So you might say average attendance, and then descriptive statistics like the min, mean, max, and so on. So I have a notebook I could show you how we would run this code. I actually ran it earlier on, but I can just show you briefly. And this is available for you to try out. We're creating a data frame here which has houses for sale features and houses sold features. And this is doing the feature engineering part of it here. You don't need to worry too much about what's happening. It's just basically computing some new features. But then to register the feature, this is all we need. We have two features. The first one is called featurestore.create feature group, and it's the houses for sale. And the second one is the houses sold feature. Once those features are registered, you can have a data scientist just needs to write the code like the following, where they say, well, I would like to have some training data with these features. And then you say create a training data set. It will create the training data set, and we can see that back here. In our training data sets, it will be in here. You can also see it in the file system if you go into the file system in here. This is the training data set here. And that's actually in TensorFlow records. And if you've ever worked with TF records, this is where the beauty of the system comes in, because you don't need to get down and dirty with TF records. If you'd looked at TF records, you would have 100 lines of code to decode them here. But we have a lot of metadata about the features, so the decoding is very simple. And then finally, you can launch and train this model as we do down at the bottom. So one last example just before we finish. I'll just show you how we did the hyperparameter optimization. This is called fashion MNIST. It's a well-known data set. And what we did was we defined these 6 combinations of learning rate and dropout rate. And then we called this code here to run the training on 6 different Spark executors. And if I go back here, we can have a look and see how that went. And this is the Spark job here. We can see the executors. There's 6 of them down here. They've finished, so they're dead. And then you can see the tensor board when you're finished, which will have all the results of your training. We can see it here. If you want to serve a model, you can then just go and click up here and say create new model serving, and then press run, and your model is now serving. Okay. So that's a quick kind of overview of the platform. If you want to try it out, and this is a summary of the platform, there's 2 places you can try it out. One, you can come to our meetup. So we have a meetup here in Stockholm. We've only had 2 events, but we already have 320 plus people in it. The next event will probably be in March, and it's called HopsML Meetup. And then a lot of people have worked on the platform. And I'm from Logical Clocks. And just to finish off, I'll leave this on screen. If you want to try out the platform, just go to this particular link at the bottom. It's a Google spreadsheet. I had a tutorial or lab here yesterday, and I asked people to fill in their name. And you don't have to fill in your email if you don't want to, but it makes it easier for me to find your address. We have hundreds of people who tried to register here. But you're going to register at hops.site. And if you fill in your name there, then I'll approve the account. I won't approve people who aren't in the spreadsheet. But then you'll get access to GPUs and a lot of storage there. So, and just one point, you'll get to create 5 particular projects. Other point, if you don't know what 2-factor authentication is, don't select it, because that's like my time is limited. And with that, thank you.